Yes, good morning, students.
Morning, sir.
Yes, now voice is audible.
Yes, sir.
Okay, 1 minute. Again, I will share the PPT. Yes, PPT is visible.
Yes, sir.
Yes, sir.
Half an hour delay. Okay, now the PPT is visible. Yes, someone has to give the answer.
Yes, sir.
Yes, sir.
Okay, thank you guys. Half an hour delay. Yes, Jai Shri Gurudev. Good morning, one and all. Today we are going to.
Good morning.
Today we are going to start our the subject dynamics of machinery in that module 1. So what is the module 1 says that is the static and dynamic force analysis. As you know that force is a vector quantity, it has a both magnitude and direction, and also we know the where the location or the point on which on the member the load is acting. These three things you are going to determine whether the body is under rest condition or under uniform motion. Then that is called a static force analysis. Dynamic force analysis means when the body is under a motion along with it accelerated. The body is accelerated. Then you go for determine the magnitude, direction, and location of forces are acting on a body. That analysis is called as dynamic force analysis. Right? Again, in detail, we'll study here. Suppose in design of machine element, before going to design of machine element, what do you mean design of machine element means? Assigning the specification of a machine component to withstand the load or to do its function. So before going to assign the specification, we should know the how much load is acting on a component. That we are going to determine in this subject. In the design of machine element, in the DME, it is imperative to know the magnitude and direction of forces transmitted from the input to the output, right? That is our aim here. Determine the magnitude and direction of forces acting on each component. That's the first thing. Once you determine, then you go for design the component. Then you go for assign the component, assign the specification of component. Specifications are, as you know, that shape, size, material composition, and arrangement of parts. These four things. Okay, remember that. Then once the force is acting on that body, when you go for assign the specification, next to judge whether the body is able to withstand the force or not. If it is able to withstand the force, whatever the stresses induced in the body is less than the yield strength or ultimate strength, then you can say the design is safe against strength. Then whatever the deformation of a body takes place when I subject it to an external force, then whatever the deformation of a body takes place, that should be less than the allowable deformation. Then you can say that the design of component is safe against rigidity. One is design against strength, second one design against rigidity. The third one is, again you go for determine one more design against, one is natural frequency. Whatever the natural frequency is there, that should not coincide with external frequency. If it coincides, resonance occur, there is the failure of a machine component takes place. That's why you go for design against natural frequency. Now these three things thing you should remember when you go for design any machine component. One is design against strength, second one is design against rigidity, third one design against natural frequency. If I say in a market or in an that component has to come to the market means then they will satisfy these condition. Okay. So before going to design, first you should know the what are the forces, the magnitude and direction of forces acting on the component. Okay. Next, in the study of dynamics, it is interested in determining the magnitude, direction, and location of forces, but not sizing the member on which they act. So in dynamics of machineries, we study only the magnitude, direction, and location of forces or movements acting on the body. Then where you go for sizing the member, that sizing of member takes place, you will study in the subject design of machine element. Clear? Next, if components of machine accelerated, means body is under motion and it is accelerated, whatever the inertial forces are developed, inertial forces is nothing but mass into acceleration, those are inertial forces, are produced due to their masses. If those inertial forces are small compared to external applied loads, they can be neglected while analyzing the mechanism. Such analysis is called as static force analysis. I think already we discussed here in lifting cranes, when lift the load, in the cranes, what happened, the weight of the bucket and whatever the components in the buckets are, the weight is more. The load is more as compared to its, the motion, the velocity, in constant velocity. That's why you neglect that motion, you neglect the inertial forces. We'll consider only the weight of a bucket and the weight of the things we're going to lift in the lifting crane. That whatever the forces are acting on the each component of the lifting crane, that analysis is called as a static force analysis. You can determine magnitude, direction, and location of forces. Suppose if inertial force is more than that weights of those component, then you'll go for analyze here dynamic force analysis. For example, when rotors rotates at high speed, best example last class I given. If you start to rotate the fan, speed number 1, 2, 3, 4, 5, you regulate it. You come to know that at speed number 1, 2, 3, you'll get there is no much noise or vibration takes place. When you start at speed 4 and 5 in a fan, you can see the more forces or noises will generated. Due to what? Due to inertial forces are greater than the static forces. There you go for determine again what is the magnitude, direction, and location of forces are transmitted in the each component, right? The static force analysis, the static is also called as a steady state force. Steady state force. Yeah. Now suppose if you want to study the go for determine the forces that may be static or dynamic. In theoretically, the body should be in equilibrium. So what do you mean by equilibrium condition means whatever the all the forces are acting on your body that is equal to 0, or whatever the movements acting on the body about an arbitrary point that is equal to 0, then it is a static equilibrium. Remember these things, okay? Say body is in static equilibrium if it remains in its state of rest or motion. If the body is at rest, it tends to remain at rest, or if it is in motion, it tends to keep the body is in motion. Means called a steady state. Means if the whatever the property of the body or the behavior of the body, in general called as behavior of the body, does not changes with respect to time. Then only you called as you can go for study the how the body behaves. That is called as the equilibrium condition. If the body is under rest position, then we will go for, or the body is under rest or uniform motion, then we will go for apply what type of equilibrium here? Static equilibrium equation. Already you are used this equation in your elements of civil engineering, right? Vector sum of all the forces acting on the body is equal to 0. Vector sum of all the movement about an arbitrary point is equal to 0. These two equilibrium equations is used for what type of body here? Body is under rest or uniform motion. If you go for next one, the body is under motion, along with it is accelerated, means velocity is not constant, velocity changes with respect to time. Then you go for apply a dynamic equilibrium equation. Again, if the body is under linear motion, means it follows a straight path. The body is move along the straight path, not a curved path, straight path. Then it called as a for body is under linear motion. Then what type of equilibrium equation will go for Old-Scoot? Here, vector sum of all the force acting on a body is equal to mass into acceleration. Mass into linear acceleration. Suppose if the body is under angular motion means you take a fan, okay, fan, mixer, grinder, a compressor, okay, the what are the parts of the IC engine, crankshaft, flywheel, all comes under what type of motion here? Angular motion. Even cams comes under angular motion. Linear motion is follower, right? Those are for angular motion. What type of equilibrium equation works good here? Vector sum of all the movements or torque about an arbitrary point is equal to I is nothing but mass moment of inertia. Is a product of mass moment of inertia and angular acceleration. Remember these two equations. One is static equilibrium, another one is dynamic equilibrium. Throughout that, our subject, we use these equations only. Okay? Is any doubt? Any doubt?
No, sir.
Okay. Next, then you go for, so what are the equilibrium equations we applied here? Well, the static equilibrium equations, vector sum of all the force equal to 0 and vector sum of all the moments about arbitrary point equal to 0. Then suppose if a member or a body is subjected to only two forces acting on a member, then how do you make it equilibrium? How do you make it steady state? Then you can see the best example here, a tug of war. The children are playing a tug of war. If they apply a
You need to
force,
balance two forces.
yeah, you apply a force in one direction here, in right side, another members are again our children are applying force another direction. Those two forces, if here see that the tag here, the tag should be in equilibrium condition means these two forces, whatever the force are applied by the children, that should be equal, right? Again, how do you remember here? Force is what type of quantities? Vector quantity. It has both magnitude and direction. Along with one more you should remember here, point of application of load. These three things you should remember. We go for, when you say when a member is subject to two forces means the forces are of the same magnitude. The magnitude should be same. Right, you can see here picture here, one more here in the this picture in general we can say that now this is a body, the F1 is acting at point A, F2 the force, another force acting at point B. Those two forces should be what? First condition, it should be a same magnitude. Magnitude should be same, means 100 Newton force applied here, here also 100 Newton force is applied. The forces should be same. That's the first condition. Second condition, direction. Force is a vector quantity. First one is magnitude. Second one is direction. Now, where you apply that load here? No, in which direction you are applying your load here? Those two forces should be in opposite in nature. Now, F1 is acting towards the body. F2 also acting towards the body. Those two forces should be acting in opposite in nature, opposite direction. And third condition, that is a line of action, where the forces are acting here. The forces act along the same line. See that F1 is acting along this line, F2 is also acting along this line. They are acting in which direction here? On the same line. Then we can say that if you satisfy these three conditions, one is magnitude is same, second one is direction should be in opposite in nature, and third one is the line of action of force should be along the same line, in the same direction, in same line. Then we can say the body is under equilibrium. And a body is subject to two forces. If you say when a body is subject to only two forces, that body is in equilibrium condition means that satisfy these three conditions. Right? This is theoretically we can say that. When come to practical also, see the example for tug of war. Okay, in tug of war also, the children are this side, in the right side, the children are applying force towards the right direction. On left side, you can see the three children are pulling the rope in left side direction, right? Whatever this, if you say that whatever the knot is there here on the thread, okay, see that should be in rest position. Then what we can say that those two forces are equal in magnitude. They're acting along the same line of action and acting in opposite direction. Remember these 3 points, right? Is any doubt about this point? If you have doubt, please ask the question. Any doubt?
No, sir.
Okay. Yes. Okay. So can you give any one example apart from this tug of war? Any member, any body is subject to only 2 forces. Yes. US number 1 is there. US number 1. 2. US number 2. 3. 4.
Sir,
Yes. 4. What's your name, man?
Abhilash, sir.
Abhilash. Now tell me, give me any one example for a member is subject to only 2 forces. Then it should be in equilibrium condition. Yes. No examples? Suppose if you are standing on a floor, okay, whatever the weight of the body is of yours is acting vertically downward towards the gravity, right? At the same time, you are in stable equilibrium means whatever that from the ground also a force is acting from the foot out from your foot to the upward. That is the 2 forces are acting. Same force should be acting, magnitude should be same, acting in opposite direction and along the same line of action. Then only you are under stable, right? Yes, Abhilash?
Yes, sir.
Yes, did you understand, ma'am? Unless you can see that when a person is unstable means, if it best example take, a person has, is taking hot drinks, they are not stable because of whatever the force is acting here, they are not going to balance their body. That is an unequilibrium condition.
Yes, sir.
Okay. Yes, use number 5. Someone may say use number 5. 6. 7. If you not give an answer means I'll put the absent here. 8. 9. 10. 11. Okay, the best example, one more example I can give here, take IC engines, internal combustion engine. Okay, I think already I have seen in your elements of mechanical engineering, 2-stroke and 4-stroke IC engine. Yes, Abhilash, use number 4.
Sir,
Yeah, so so who has taken that elements of mechanical engineering for your section, ma'am?
sir.
Yeah, who taught it?
Sulkapa sir.
Sulkapa sir, Professor Sulkapa sir has shown that model, 2-stroke and 4-stroke engine model. Have you seen that?
Sir.
Yes, say yes or no. No? Or you during?
No, sir.
No. Okay, in kinematics of machine also, I think Professor Viresh Chandra has handled, right? For your section. Yes or no?
Yes, sir.
Yeah. You have seen that model, 2-stroke and 4-stroke model or slider crank mechanism.
sir.
Have you seen that video? Slider crank mechanism.
Yes, sir.
This slider crank mechanism, it contains one is crank, right? Second one is connecting rod, and third one is piston, right? And the last one link is a fixed link. Now, which link is subject to only 2 forces? Can you give me anyone? Anyone can give the answer. In IC engine also, a pressure is applied on the piston, right? Once a pressure is applied on the piston, the piston is subject to only two forces, or another piston is connected to connecting rod. Connecting rod is subject to only two forces, or crank. The crank is subject to only two forces. Which part of the slider crank mechanism is subject to only two forces?
Crank.
Yes? Yes, use number 12, 13, 14, 13. Give me the answer, ma'am.
12, sir.
Use number 12. Yeah, give me the answer.
Connecting rod, sir.
Yeah, yes. Connecting
Connecting rod.
to only two forces. Good, ma'am. If it is stable or under uniform motion, one force is applied from the piston on the connecting rod. Another force is coming from the crank to the connecting rod. Only the connecting rod is subjected to only two forces. Good, ma'am. Yes. Now that is how a member is subject to only two forces. Remember these 3 points. How do you remember these 3 points? Means force is a vector quantity. It has magnitude, direction, and the location of force. When you say the member is subject to only two forces, means its magnitude should be the same, acting in opposite direction, and the acting along the same line of action. Remember these 3 points. Okay. Next, suppose if the member is subject to three forces acting on a member, then I want to make it in equilibrium condition. How do you make it equilibrium condition? Means whatever the resultant force is zero. What is the resultant force? How do you get? By drawing a force polygon. See here, if you say the force polygon, if the force polygon, see the resultant force is zero here. F1 is acting here, F2, F3. It should be a closed one. If the force polygon, if you draw a force polygon, it should be a closed one, then there is no resultant forces, right? The resultant force should be a zero. That's the first condition. Second condition, the line of action of forces intersect at a point is known as point of concurrency. This is a very, very important one. For example, take in general here, consider a body subject to force F1 at point A, F2 at point B, F3 at point 3. These three forces, their magnitude is different. Their direction also different. It may be towards the body or away from the body. The magnitude is different, direction also different. But what is the common point here? The line of action of forces. F1 is acting in this direction, F2 is acting here, F3 is acting. The line of action of these three forces should be meet at a point. If it meet at a point, that point is called as, the point here it is O. The point is called as a point of concurrency. Then only you can make it is in equilibrium condition. Now remember these 2 points. When a member is subject to three forces, means the resultant force should be a zero, and the line of action of all the forces should be meet at a point. That point is called as a point of concurrency. Yes. Best example, see that. So if you want to draw the force polygon for here, F1 is acting at point A. See it's a force is a vector quantity. It has both magnitude and direction. How do you draw the force polygon? We'll go for take the scale. So much of Newton is equal to 1 centimeter. Then draw a line which is parallel to F1, the line of action of force here in this direction. Draw a line parallel to that one. The length of the line shows what? The length of the arrow, the length of the line shows the magnitude. The arrow mark shows what? Direction. Here, what direction here? F1 is acting downward, right? Let's just show downward. This is point we call as OA. From the point 1, you take either clockwise, clockwise or counterclockwise. You take here. I consider as a clockwise forces. F1 is acting downward here. F1, right? After that, the length of the line shows magnitude. The arrow mark shows direction, right? Now, next one is if it comes to a clockwise, F2 force is acting here. From this is a tail point, this is a head point. This is a tail and head, right? From the head point of here, F1, draw a line which is parallel to F2. Draw a line which is parallel to F2. Along that line, measure the length by taking a scale. 10 Newton is equal to 1 centimeter. Then measure the length along that F2 direction. Then the length of the line shows the magnitude and the arrow mark shows the direction. See, the direction is here at point B. Then from the point, the head here, draw a line which is next. What is the next force? F1 over F2 over. Next force is F3. Draw a line which is parallel to F3. Right? The length of the line shows the magnitude. Arrow mark shows the direction. Now it should be a closed polygon. Then only you can say that the result. No, there is no resultant force acting here. Then the body is under, and those three forces acting at a point. That point is called point of concurrency. Then the body is subjected to three forces member. It should be under equilibrium. Best examples, take a nut, a hook, right? Is a hook is subjected to two forces here. It's already fixed one. One force is acting in this direction, another force is acting in this direction. Now what happens here? One more force here. All these three forces are meet at a point that is called point of concurrency. Another best example, consider here hook, crane hook, right? In the crane hook, one force is acting here, the rope is come here, other two directions also, it may be lifting the load. We'll use what we call ropes or wires, right, to lift the load. Again, the crane hook is subject to how many forces? Three forces. If I want to make it stable, then all the three forces, the line of action of forces should be meet at a point that is the point of concurrency, and there is no resultant forces acting on the body. Yes, any doubt? Can you give the best example for this? Which member is subject to three forces in slider crank mechanism? Use number 13 because we have shortage of time. Use number 13, 14, 15, 16. Okay. Now this is how a member is subject to three forces, means if it is in equilibrium means all the three forces, there is no resultant forces, and all three forces, the line of action of forces should be meet at a point called a point of concurrency. Next, last one is a member is subjected to two forces and a torque. First case, a member is subject to only two forces. Second case, a member is subject to three forces. Now the third case is a member is subjected to two forces and a torque. Now you can see the sketch here. You can see the sketch here. A member is subject to three forces. Sorry, two forces and a torque. Best example here, a crank. Crank in a slider crank mechanism. One force is acting from the connecting rod to the crank. Another force is acting from the fixed frame or fixed body to the hinge here. Now when this force is acting here, F1 and F2 are parallel to each other but acting in opposite direction. If you rotate, this makes to rotate in what is the counterclockwise direction. If I want to make it equilibrium, a clockwise torque should be applied. What is a torque? Torque, as you know, that force into distance. What distance here? Perpendicular distance. That is a torque is equal to force into distance. Now what are these two forces? F1 and F2 acting on the hinges should be a same magnitude but acting in opposite direction and parallel to each other, not on the same line, parallel to each other. Then torque is equal to force into distance. Either you can take F1 into H or F2 into H. There should be Newton meter, where H is nothing but perpendicular distance between F1 and F2. Now when you say that a member is subject to two force and a torque, when you say the member is subject to two force and a torque, the forces are equal in magnitude, that is F1 is equal to F2, parallel in direction, means there is not acting the same direction, same line of action, acting different line of action, but should be parallel, and opposite in sense. You can remember force is a vector quantity, it has both magnitude and direction along with that line of action. Remember these 3 points. The second point you should remember the forces from a couple which is equal and opposite to the applied torque. Now what are the forces F1 and F2 that is trying to rotate the crank in what direction here? In counterclockwise direction. If I want to make it a equilibrium, a clockwise torque should be applied. Then it is under equilibrium. Best example practically you can see that take a pencil, you hold the pencil at the one end and another end you just apply a force. Then what happens? The pencil rotate about the fingers. See that here. Now again a crank is subject to two forces. One force is here external applied force, another at the hinge. It is subject to rotate in counterclockwise direction. I want to make it equilibrium means a clockwise couple should apply. Similarly, what are the examples here? Door or almirah handles. If you go for door and almirah handles, if you turn that handle, you are going to apply a torque, or you are going to apply a movement, a force, eccentric force on the lever, right? That is opening and closing of the door handles or almirah handles. And which in IC engines or in static crank mechanism, which part is subjected to a two force and a torque here is a crank, right? Now these are the three equilibrium equation you should remember. One is a member subject to two force and a torque. Second one is a member subject to three forces. Then third one, a member subject to two force and a torque. If you understand thoroughly these three basic things, basic equilibrium equation, then you can easily solve the problem for study the what is the 4-bar mechanism, for static crank mechanism, how do you make it equilibrium, and all those things we'll study. Yes, any other doubts? Now you can ask me the doubt. Yes, use number 46. 46.
Yes, sir.
Yeah, now give me any one practical application, man. For two member subject to two force or two force or three forces or two force and a torque. Yes.
Sir, when we open the laptop, sir.
You open.
Laptops.
Okay, when you open the laptop.
Two force on the top.
Two force
Yes, sir.
and a torque. Next. Yes, use number 50.
Yes.
Use number 50 is there. Kiran Kumar.
Yes, sir.
Oh no. So what you are doing, man?
Yes, sir.
Give me example for a member subject to only two forces
Hello.
or three forces or a two force and a torque. Yes. You not listen the class, man?
Sir.
Huh? Use number 42.
Sir.
Use number 42.
Sir, stretching a rubber band.
Yeah,
Stretching a rubber band, sir.
Consider which?